I'm Silvia Newell. I'm the director of Michigan Sea Grant. I'm also a professor at University of Michigan, and you'll also be hearing from Nate Manning, who's the director for the National Center for Water Quality Research at Heidelberg University in Ohio. And you might wonder why I dragged somebody from Ohio up here for this, but they've been monitoring the River Raisin for the last 42 years. And so I'm going to talk to you a little bit about the blooms in Lake Erie, and Nate will talk to you a little bit about the loading from the Maumee River and the River Raisin, and then I'm going to talk to you a little bit about other nutrient policies and how we're getting close to them or not. Okay, so as I'm sure everyone who's looked at the news here in the last 20 plus years has noticed, there are algae blooms that happen in Western Lake Erie every summer. Sometimes the scum's so thick you can literally reach out and hold a scoop of algae in your hand. Sometimes it just looks like somebody spilled green paint on it. And sometimes it looks fine and you wonder what all the fuss is about, depending on the year and where you are. And the bloom moves around a lot. As you can see from this slide here, we got water coming in from the Detroit River up at the top, water coming in from the Maumee River at the bottom. Notice that the Detroit river water coming in is like pretty blue, right? That 95% of the water comes in from the Detroit River, and about 5% comes in from the Maumee, but there's such heavy nutrient loading from the Maumee River, that's why it's all bright green there in Maumee Bay. And every year then there's a projection for how big the bloom is going to be that NOAA does. A guy named Rick Stumpf out of Maryland creates this projection based on the Heidelberg National Center for Water Quality Research, that is a mouthful, spring loads coming out of the Maumee River, or how many nutrients are coming from the river. And so you can see that for this year, they predicted a sort of middle-sized bloom. And we actually ended up, I think, towards the bottom of the predicted range, which is great. So every year, NOAA evaluates the severity of the bloom based on the size and extent of the bloom. And you can see that it started off being maybe not great, but not so bad in the early 2000s. Then it got real bad. I'm sure everybody remembers the Toledo water crisis in 2014. There was actually a much bigger bloom in 2015, and it's been sort of on a downtrend mostly since then, since we've been putting together a bunch of different management practices to try to mitigate the problem with these blooms, which is great. Because the blooms are caused and driven by nutrient loading in the spring. It's both because that's when we apply fertilizer, but also because that's typically when we get the biggest storms, right? It's pretty dry out right now. If you drove over the River Raisin today, it's pretty low. Rivers are pretty low right now, but as you know, they get high in spring. We get a lot of precipitation, and that drives runoff from fields, which everyone who's ever tried to keep soil on their field knows. And you can see here that there's a relationship between the amount of total phosphorus, the amount of dissolved phosphorus, and this is the amount of nitrogen in a form we call killed-all nitrogen, which is everything but nitrate nitrogen. So if you apply UAN on your field, it's the U and the A, but not the N.
My name is Nate Manning. I am the Interim Director of the National Center for Water Quality Research at Heidelberg University. And I'm going to spend a little time today talking to you guys about what we're seeing in the western basin of Lake Erie's tributaries, right? So the rivers that feed into the lake, sort of the trends that we're seeing in some of the important nutrients that really drive the harmful algal blooms in Lake Erie. So a little bit about us. We're at Heidelberg University in Tiffin, Ohio, about an hour south of Toledo. We run a program that started back in 1974 called the Heidelberg Tributary Loading Program. We sample across Ohio and in Michigan, the River Raisin, which I'll be talking a bit about tonight. We currently sample at 23 different locations across Ohio and Michigan. And you can see most of them are in the Western Lake Erie Basin, right? So 16 of the locations that we monitor of the 23 total are in the Western Lake Erie Basin. We also have some in the Central Basin with the Huron and the Cuyahoga. And so you can see the little H's here are all of our different monitoring sites in the Western Basin of Lake. So we try and get our monitoring stations as close to the end of the watersheds as we can. Generally, we try and piggyback off of the USGS gauging station for that river. If you've ever been driving past the river and you see the little building on the side of the road, like the one in the picture there, it's most likely a USGS gauging station. And if you're in Northwest Ohio or Southeast Michigan, there's a good chance that our equipment is in there as well. We have refrigerated samplers that take samples 3 times a day, year round. And for the Sandusky and the Maumee River, that data set goes back to 1975. So daily data going back, 50 years now almost. For the River Raisin, it goes back to 1982. So that was one of the earliest rivers that we added after the program really got up and running. We retrieve the samples every week. We have a bunch of technicians that go out and collect these drums from the samplers once a week, and they bring that back to our laboratory where we do all the chemical analysis for our data. We do totals, so total phosphorus, total nitrogen. We do particulates, so suspended sediments, as well as all the dissolved fractions. So, the phosphoruses and the nitrates and nitrites and the things that you hear about when it comes to Lake Erie issues. We also, we do ion chromatography and colorimetry for those in our lab, and we develop lots and lots of data, right? So in that upper right-hand plot is, a year and a half in the life of dissolved reactive phosphorus, and I think that's the Maumee, right? Each one of those data points is a day, and then we condense that data, right? That yearly data down into a single point to look at long-term trends, right? So we can look at variation within year with our daily data. We can look at long-term trends with our annual data. The Western Basin of Lake Erie has a number of what are the Great Lakes Water Quality Agreement Annex 4 priority target watersheds. You can see the ones that are in, the different browns and pinks there. The Raisin and the Maumee and the Sandusky are the ones that I'm going to be talking about tonight. They're sort of the largest of the American tributaries to Lake Erie, and they're really where a lot of sort of the issues that we see with nutrients sort of come from. So all of that phosphorus and nitrogen that comes off of the fields or off of the cities or whatever sources ends up in the lake, right? And that March to July, particularly the spring loading from the Maumee and the Raisin and the Sandusky, are linked to the bloom severity out in Lake Erie, right? So how bad the harmful algal bloom is really depends on the spring phosphorus load, right? And you can see when load is high, the brown lines on there, right? The bloom is bad. So 2011 was particularly bad, right? But 2012, it was low, right? There was low phosphorus loading, and so we saw a small bloom. And we see that pattern repeating. High loading years cause big blooms. Low loading years cause small blooms. And so as I'm talking about things tonight, I'll be talking about load and concentration, right? And so those are two different sides of the coin when it comes to nutrients and trying to track them in these rivers. The load, could think about it as that packet of sugar, right? It's the ultimate mass of whatever constituent that you're interested in, right? In our case, we look at metric tons of phosphorus, metric tons of nitrogen per year. That's the load, that number, whatever that number is in metric tons. The concentration, however, is that load dissolved into some liquid, in this case, water, right? The water in the rivers. And so you can have the same load and very different concentrations, right? If you pour that packet of sugar into a cup of coffee, it's going to be way more concentrated than if you had poured it into a big pot of coffee. And so that's sort of what we see with the Maumee, really high concentrations, because the load is equivalent to, the bigger rivers up north, like the Detroit, but in a much smaller volume. And so it's important to track both of those, right? To know how concentrated these constituents are in the water, as well as just the total mass of the constituent being transported. So talk about load and concentration. And when we look at the loads around all of the different watersheds that we monitor, right? The Western Lake Erie Basin ones, right, actually look fairly low if you compare them to some of the Ohio River, right, the Scioto and the Great Miami, and then the Grand Lake St. Mary's tributaries like Chickasaw and Coldwater, right? And so the loads are different, right? The loads are lower, but, right, the concentrations may be much higher in certain instances. And when we look around the lake, the western basin of Lake Erie, we see a really unique pattern in how the watershed nutrient loads are distributed, right? If we look at suspended sediments as we move west to east from the Raisin to the Cuyahoga, right, we see increasing suspended sediments. Nitrate, nitrogen, as well as dissolved phosphorus have this sort of pyramid shape, right, where they peak in the central basin, or in the eastern edge of the western basin, with the Sandusky, Rock Creek, Honey Creek, and then fall off as they move into the central basin. Dissolved phosphorus has that same pattern, and the proportion of TP as DRP. Basically, how much phosphorus that we're seeing is the dissolved fraction, is the part that is sort of bioavailable. So a higher ratio of bioavailable phosphorus is bad for the lake, right? Is bad for the harmful algal blooms, and we see, right, higher percentage of DRP in these western basin tributaries, the Raisin, Maumee, and Sandusky. So why do we see this pattern? A lot of it's just land use, right? There's a lot of cultivated crops in the western basin. They're high across all the watersheds that we measure in Lake Erie, except for the Cuyahoga, right? The Cuyahoga is Cleveland, Akron, Canton. It's a lot of urban area that we don't see in the western basin. And looking at different combinations, right, of sort of landscape use and things like slope and soil types, right, we can sort of generalize into three different categories that explain sort of all the variation, right, up to 85% of the variation that we see in the different loads across these different rivers. One group, low slope, lots of hydrologic soil group C and D, corn and soybean, right? These are the row crop agriculture watersheds. The others are another one is high slope, right? This is the urban Cuyahoga, right? Cuyahoga watershed, more urban and point sources, really flashy, right? As soon as it rains, right, the river reacts very quickly. Whereas we also have these sort of low to moderate slope, more pasture and livestock, low flashiness, very slow reacting rivers, right? And so when we look at these sort of in relation to, how much bioavailable phosphorus is there versus how much sediment do we see in these watersheds, right? They sort of can break down into three different groups. Groups in the upper left, right? Management practices, you're worried about nutrient leaching and soil stratification. In the lower right, right, you're more worried about losing soil, right? So erosion control is more important. And if you're in that green box, right, both of those are important. You need to have management action that tackles both nutrient leaching and soil erosion, right? And so it can be difficult. And then we look at our different watersheds around Lake Erie, right? We see the Raisin here in the left-hand corner, lots of bioavailable phosphorus, but less sort of loss of sediment, right? The Maumee and the Sandusky are in that green one in the upper right, where it's sort of both. You sort of have to worry about sediment and nutrient loss in those watersheds. So to get to these watersheds and talk about sort of what we've seen in the last 10 years or so, in the Sandusky, when we look at annual loads, so on this plot, the red line is total phosphorus load. So how much in tons of phosphorus is being exported by the Sandusky. The black line down at the bottom is the dissolved reactive phosphorus load. And the blue bars are discharge, basically how much water is flowing through the system. And you can see total phosphorus follows discharge very closely, right? The more discharge you have, the more sediment you have, the more sediment you have, the more total phosphorus, more particulate phosphorus you have. Dissolved reactive phosphorus is fairly flat over the last 10 years, right? We're not seeing much change in the total load being exported by the Sandusky into Lake Erie, even though the total phosphorus load has gone up. We now look at the concentrations. Essentially, have concentrations changed, even though the loads may not have. Again, same sort of pattern we see. Not much change in dissolved reactive phosphorus concentrations, but an increase in total phosphorus concentrations across the past 10 years in the Sandusky. In the Maumee, which is really the major source of phosphorus and nitrogen to the Western Basin, again, same sort of pattern on the graph here. What we see is total phosphorus is flat when we look at the annual loads. Discharge has gone down. Discharge has gone down fairly significantly over the last 10 years. And dissolved reactive phosphorus has followed that, right? Has decreased a similar amount as what we're seeing with discharge. And when we look at the concentrations, total phosphorus concentrations are creeping up on an annual scale. And dissolved reactive phosphorus is fairly flat to slightly down over the past 10 years. Now, when we look at just the spring loads, and if you remember back to the beginning, I said the spring loads from the Maumee are really the thing that drives a lot of the harmful algal bloom intensity. We see a slightly different pattern, right? We again do see a decrease in discharge, but total phosphorus concentrations have gone down as well. And the dissolved reactive phosphorus concentration has gone down more than we saw in the Sandusky, to the point where, we are getting close to that black line, to that target line, but most of that seems to be because of the decrease in discharge, right? So if we see another really high discharge year, we would expect dissolved reactive phosphorus and total phosphorus to rise with that as well. In the spring flow weighted mean concentrations, again, TP's creeping up slightly, DRP's down, but not down as much as we would like when we take the effective flow out of the equation. And these plots, I just wanted to show that the increases that we're seeing in TP on the right-hand side of these graphs, most of the increase that we're seeing is at high flow, so storm events. Anything above the 90th percentile discharge is where we're seeing the majority of increases in total phosphorus concentrations. Finally, the River Raisin. River Raisin is also a Great Lakes Water Quality Agreement Annex 4 priority, and so has those 40% reduction targets in place for TP and SRP, similar to the Maumee. We measure, our station is in Monroe, or at least near Monroe, and we've been monitoring again since 1982. We have about 95% of the watershed above our sampling site, so we feel pretty good that we're getting the majority of the water and the nutrients coming out of the raisin at our site. So these are a little different. I'm going to show for the raisin just the load and the concentration side by side, just because it's easier to see how similar the patterns are in both the load and concentrations for these. For total suspended sediments, basically how much sediment is being transported out of the watershed. We saw a big spike in sediment transport between 95 and 2000. And then a big reduction, right? Both load and concentration of sediment went way down until about 2015 and has sort of steadily been creeping back up ever since then. Just in the last 10 years, we've seen, somewhere in the neighborhood of a 25% increase in sediment concentration and sediment load out of the raisin. For total phosphorus, if you look at it, sort of squint your eyes, it's actually pretty flat, right? We're sort of back to where we were in the mid 80s for total phosphorus in a lot of cases. We have sort of a W-shaped response, right? We had decreases through the 80s and 90s, increases until the mid 2000s, decreases again until 2015, and then since 2015, the last 10 years or so, we've seen a pretty significant increase in both the annual load and the flow-weighted mean concentration of total phosphorus in the raisin. Soluble reactive phosphorus, again, sort of the one that everybody pays attention to when it comes to the HABs. You can see an increase starting in the early 2000s in both concentration and load, and it's been sort of flat since about 2010 in both of these cases. There is some evidence of a downturn in the past 5 years, but we need a little bit more data to sort of be able to do some of the analysis that we do to make sure that that downturn is significant. But there is some positive sort of evidence for a reduction of SRP out of the raisin in the last 5 years or so. And nitrate, another one that's been of interest to the harmful algal blooms. There's been a trend in the last 5 years or so also with nitrate of decreasing concentrations and loads. But again, we need another couple of years to make sure that's a real trend, right? And not just a figment of a couple of years. And so in summary, I want to say that annual loads that we're seeing from these Western Basin tributaries, particularly the raisin, are increasing for a lot of these nutrients of concern. The flow-weighted concentrations, though, tend to be fairly flat, right? And so a lot of that may just be tied to how much water is being moved through these systems, right? We're seeing increasing TP and TSS concentrations, which is worrying, but not, I don't think that the rate that they're increasing is anything other than just changes in discharge. It does suggest that we're seeing increased particulate phosphorus loading. And it's important to note that in these rivers, the spring loads, just what comes through March through June, March through July, can be up to 70% of the annual load, right? So most of what we're seeing come out of these rivers is coming out in the spring. And we are still exceeding Annex 4 recommendations, though in a few places and in a few cases, we are getting close.
So I'm going to switch gears a little bit and talk to you about not just phosphorus, but also nitrogen. So, right, you add nitrogen to a field the same way you add phosphorus to a field. Well, maybe you physically apply it differently depending on what kind you're adding, but both nutrients are important for crops. Just like any other kind of balanced diet, if things get out of whack, we get a problem. And back in 2015, the US EPA started moving towards dual nutrient control, meaning controlling for both phosphorus and nitrogen. This happened after the Great Lakes Water Quality Agreement, after the Annex 4 40% targets for phosphorus were set. And at that time, I think I was probably the only person doing nitrogen research in the Great Lakes region, really. So there just wasn't a lot of knowledge about it or how it might be applying to our Great Lakes. But the reason that we care about this is that if you add phosphorus and nitrogen together, you can get very large, very toxic blooms. If you reduce the nitrogen but leave the phosphorus really high, you end up with little algae that can pull nitrogen out of the air the same way that your plants can pull CO2 out of the air. They fix nitrogen from the gas that's in the air at 79% of what you breathe. And it takes a lot of energy to do that. So the blooms might get big, but they don't really get toxic because there's no extra nitrogen around to make the toxin. Because the toxins that we're talking about, like microcystin, for example, has about 10 nitrogens per molecule and no phosphorus. So if you have really low phosphorus, you might have a low bloom because you don't have enough stuff to build all the cells. But if you have a really high nitrogen in comparison to your phosphorus, you still might end up with pretty toxic cells because they got all this extra nitrogen around they got to do something with. So ideally, we'd have small and not very toxic blooms. That would be the goal. And to do that, you have to reduce both nitrogen and phosphorus. And we're seeing this in the blooms that we see in Lake Erie, where back in the 60s and 70s, the kinds of what my advisor used to refer to as little green jobbies that showed up in Lake Erie were different. They could pull that nitrogen out of the air and they could use it. But now what's there doesn't need to. There's plenty of extra nitrogen around, so they just don't bother. So the kinds that live there now, this is showing a bunch of microcystis colonies, which is like the dominant kind of algae that we see in Lake Erie. They don't need to be able to have the genes to pull the nitrogen out of the air because it's really expensive. It involves breaking this triple bond between two nitrogens that requires a lot of energy. It's just not worth it. And we got plenty of extra nitrogen around between adding plants that can fix nitrogen and adding nitrogen fertilizer and back in the day, especially a lot of point source treatment. We've added a lot of nitrogen to the world. And so there's just plenty around. They don't need to fix it anymore. And we started shifting away from nitrate as a fertilizer, or like more nitrate in fertilizer in the mid-90s. As I recall, after the Oklahoma City bombing, it got a lot harder to buy ammonium nitrate. And so we switched to other things. And then it turned out other things stayed in the soil better. And so we started using urea ammonium nitrate and anhydrous ammonia. And when we did that, we started shifting the kind of nitrogen that we see in the river. So this is from the Heidelberg data set that Nate was talking to you about. And it's showing the kind of nitrogen that we see in the 70s and 80s versus 90s versus post-2000. And this is basically the percentage of the nitrogen load that's not nitrate. So it's everything other than nitrate has been increasing in how much of the load it makes up. In other words, nitrate, which is kind of hard to use, it's expensive, it's got a lot of oxygens on it, versus the stuff that's really easy to use, like urea and ammonium. Those are really good for cyanobacteria. They like them a lot. We've seen a lot more of them. And we've seen a lot more really toxic blooms, bigger, more toxic blooms with that addition. And so a collaborator of mine, a guy named Hans Pearl, decided to do some experiments in a project we're doing last summer and the summer before that. And he was like, all right, well, if we reduce phosphorus by 40%, how much do we need to reduce nitrogen for the bloom to not be big and toxic, basically? And so he did all these mesocosm experiments over at Stone Lab on Put-in Bay in Lake Erie. And they basically figured out that we need 40% reduction for nitrogen the same way that we need it for phosphorus. The really good news about this is that nitrate at least is going down at the same rate as the SRP that Nate was showing, at least in the Maumee River. So a lot of the same practices that we are using to reduce phosphorus also reduce nitrogen, fortunately. And while the nitrate is higher, still it started higher. And so it's going down at about the same rate. We just have a little longer to get there. But a lot of the things that we've been doing, like adding in wetlands, riparian wetlands, edge of field strips, saturated buffers, grass waterways, all of these things. This is showing a wetland in Ohio that's part of the H2 Ohio project. It's around Grand Lake St. Mary's, and it's showing how much the wetland reduced dissolved phosphorus, total phosphorus, nitrate, and total nitrogen. And you can see it reduced all of them. It's a small wetland, so they're in kilograms. So thousands of kilograms as opposed to like metric tons for the whole river. But still, it's reducing all of the forms of all the nutrients that we really need to be worried about. And this is with my collaborator, Stephen Jackman, who's at Wright State Lake Campus around Grand Lake St. Mary's. And then he also installed the saturated buffer. And back to Nate's point about load versus concentration, this is just looking at concentrations here, but he put a saturated buffer, so it's a stop log, cut the tile, put in controlled drainage at the end, and then in this case, he actually shunted it sideways into 2 pipes and then planted a bunch of plants over it, essentially. So it was not expensive to install. It didn't require a whole lot of maintenance, but it broke the tile and shoved the water sideways into feeding the plants instead of letting it go into the ditch. And we compared that to the watershed next door. It reduced the concentrations of everything, both dissolved reactive phosphorus and nitrate, seriously in every season. And that was pretty exciting, actually, because the field that he put it on, the slope was supposed to be too great for this to work well in. It was, more sloped than the USDA recommendations. Worked great. Yeah, and it cut back about 70% of the water, too, held it back in the field when it was needed, and the water just moves through and over the stop logs in the spring, so no plants drowned, the yield was increased, and everybody was happy.